Today we're going to talk about Chapter 5, Section 6 in our book, Finding Rational Zeros. So, we see a polynomial function, and I'm telling you that it has the following zeros. It has negative 5 halves, negative 3/4, and 7/8 as zeros. Now, you may or may not notice, but the numerators of these are factors of our constant term, that negative 105, and our denominators, 2, 4, and 8, are factors of the leading coefficient, 64. This will always occur. We have what's called our Rational Zero Theorem. So essentially what this is, we have our factors of our constant over factors of our LC, and we just have to keep in mind that factors can be the positive or negative version of each of these numbers. So let's take a look. Let's list all possible rational zeros. Now notice I'm saying rational zeros. These are not necessarily going to be all of the possible zeros. You can still have irrational zeros. This just helps you kind of shorten your possibilities so you don't have to test every single number. So we have, let's make our list. Positive, negative factors of 12, which are 1, 2, 3, 4, and 6, and 12, of course. And then factors of our leading coefficient, which are just 1. So I'll take these and over positive negative 1, so I'll have positive negative 1, positive negative 2, positive negative 3, positive negative 4, positive negative 6, and positive negative 12. Those are the only possible rational zeros for this polynomial. Now let's take a look at the other one. So, positive negative factors of 10. So we have 1, 2, 5, and 10. And then factors of 4, 1, 2, and 4. So we've got to take every single combination. Now the other one we just had 1, so here just be strategic, be smart, take one of the denominators and just exhaust that list. So let's go with 1 first, so positive negative 1, positive negative 2, positive negative 5, positive negative 10. Now let's go with the 2, positive negative 1 half. 2 over 2 is the same thing as 1, positive negative 5 over 2, and positive negative 10 over 2 is the same thing as 5. So now we've got to look at our 4, so positive negative 1/4, positive negative 2 over 4 is the same thing as 1/2, positive negative 5 over 4, and positive or negative 10 over 4 is taken care of by the 5 over 2. So these are all of the possible rational zeros for this second equation. Let's see how we might use this. Now in 5.5 we found zeros when 1 zero was known. So we used that as our starting point, we did synthetic division, and went from there. But here, I'm not giving you one of the zeros. You kind of have to use your list, test possible zeros, and hopefully you don't have to test too many before you get something that works. Remember, you have a 0 if our remainder is 0. So let's take a look. With leading coefficient of 1, makes it kind of nice. We know that our possible zeros are 1, 2, 4, 5, 10, and 20. Now do yourself a favor, we're doing synthetic division, so test your small numbers first. So let's test positive 1. So we have our coefficients. We notice we are not missing any degrees, so we have 1, negative 8, 11, and 20. So, as we did before, drop down, multiply by 1, we have 1, add negative 7, multiply, so we have negative 7, 11 minus 7 is 4, 4 times 1, okay, so that's not going to work. 1 does not work. Let's try negative 1. It's the nice thing, at least, typically 1, negative 1, or 2 or negative 2. Your first couple that you try, one of those should work. Unless you're very unlucky and you have a very unfair equation. So let's try negative 1. Drop down the 1, multiply. And we have one that does work. So We'll factor our polynomial at this point, see if we have something that factors or if we have to continue with synthetic division. Now I have a 0 of -1, which remember that means that we have x plus 1 as our factor. 0 is our remainder, 20 is our constant, so plus 20. We have -9x and x squared. Now I'm looking at this, I'm thinking, okay, get a product of 20, sum of -9, I know that's going to be x minus 5, x minus 4. So I know my zeros are -1, 5, and 4. Now when our leading coefficient is not 1, our list is extremely long for the most part. So, our possible zeros for this one are all of these. That's pretty long. When our leading coefficient is not 1, we use our graph to kind of narrow down what's reasonable. So we're looking at our graph and we kind of eliminate a lot of those. We see there's no whole number zeros, so all of those are gone. And then we kind of base everything off of just an approximation. So we can get down to -3/2, -1/2, 3/5, and 12/5. Now again, just because these are the only rational zeros does not make those the only possible zeros, so you still have to check with synthetic division whether or not they work. So let's try with that -3/2, and well, it doesn't quite work. With the -1/2 though, we do get a 0. So just like we did with the other one, we will factor. With a 0 of -1/2, we have x plus 1/2, and then we'll go with the rest of our equation. We have 10x to the third minus 16x squared minus 34x plus 24. Now, when I'm looking at that, I see, well, 2 factors into all of those. So I'm going to factor out my 2. Doesn't make 2 a 0, just means that, 2 goes into all of those. 2 out in front. Now I see that, well, I can multiply my 2 through my first binomial just to kind of make it look more like something that we see as it would factor. It won't change what my 0 is, but it'll just make it look nicer. Now from here, we need to repeat our rational zero theorem. So, factors of 12, 1, 2, 3, 4, 6, and 12 over factors of 5. Now there's something that works out in our favor, that factors of our second manipulated equation, this 5x cubed minus 8x squared, etc., anything that is a 0 there, that is also a 0 in our first equation, those are the only ones that we really need to look at. So, the ones that we saw in our original equation, the list was kind of long, but we saw that there's a couple that repeat. So the ones that repeat, we see that out of our reasonable ones, we see 3/5 again. So, let's try it out with 3/5. Let's do our synthetic division, and we can use our new smaller equation. So, 3/5, 5, -8, -17, and 12. Drop down the 5, multiply by 3/5, add, and we got lucky, it worked out. So let's factor out that 3/5. So far we have 2x plus 1, x minus 3/5, 5x squared minus 5x minus 20. Now here I see that there's a common factor of 5, and that'll get rid of that 3/5 nicely to make it look like something, something we're more used to. And I'm just going to go ahead and put my 5 next to it, so I know that I'm going to multiply that through. Now I'm looking at this and we see, well, we need a product of -4 but a sum of -1. I can't really think of a way that would factor, so our good old quadratic equation could come in handy, which is, again, opposite of b plus or minus square root b squared minus 4ac all over 2a. So when we do that, let's substitute. So we have -1. Plus or minus square root of 17 all over 2. Well, no wonder it didn't factor, because that's not rational. So our real zeros for this problem, though it took a little bit, we have -1/2, 3/5, 1 plus square root of 17 over 2, and 1 minus square root of 17 over 2. If you wish to group those last two as a plus or minus, go ahead. Just make sure that you see that those are, in fact, two different zeros. So, with that, we'll kind of close this up, and then we'll work on this more in class. Thanks for watching.